Hello, and welcome back to Workbench Wednesdays. Wait until you see this board that bucks higher voltages down to 5 volts. When I test the output with a DMM, it measures 5.02 volts. But guess what? The DMM is lying. That board's DC rail is terribly noisy. On a scope, that same point has almost 4 volts of transient noise riding on top of the 5 volt rail. This measurement is a classic example of why you need to use a scope to measure a switch mode power supply's output. In this episode, we learn how to correctly measure ripple voltage on an oscilloscope. Let's go measure. Before we talk about how to measure ripple, we should probably discuss what it is. Ripple voltage is also known as PARD, or periodic and random deviations of a DC voltage. We see it as deviations caused by periodic sources like a switch mode converter's switching frequency and random sources like thermal noise. The difference from the top to the bottom of the waveform, or the max to min voltage, is the ripple voltage. In other words, ripple is the AC component of a DC voltage. To measure it, we need a few things. DMMs are great, but they're slow and they convert AC into RMS, which is why it measured 5 volts for that board. Here's what you need to really measure ripple correctly. First, a bench power supply for input, an electronic load for output, and an oscilloscope with probes. A traditional 10-to-1 passive probe works okay, but later I'll show you one that's a little bit better. Just in case something goes wrong, you want a power supply that can limit the current. An electronic load makes it very quick to measure various current amounts. Alternatively, you can also use low-value, high-wattage resistors like this 10-watt ceramic and 20-watt TO220 package. If you did not know that resistors come in a TO220 package, then check the show notes over on the Element 14 community for a link to those. Okay, with that basic setup, now we can talk about what we have to do to correctly set up the oscilloscope. For this section, I'm using a variation of the switch mode board I showed earlier. This one has proper ground pores instead of traces, so it should be more well behaved. So let's see how good it is. By the way, on the electronic load, I set it to draw a constant 1 amp. Also, even if you don't have this particular oscilloscope, most modern digital scopes have the same controls around the same places that I'm going to show, so you should be able to follow along. Okay, let's start off by measuring things with a common passive 10-to-1 probe. Super common mistake is to simply connect the bench power supply to the input and the scope to the output, and then turn on the power with nothing else. While you might get a voltage out and you get a peak-to-peak measurement, this is almost certainly an invalid state for the SMPS. Switching converters need a load, even a small one, to correctly regulate themselves. In general, 1 kiloohm is enough to stabilize the output, but check the datasheet for your converter. Also, keep in mind you probably want to load the converter down with more current because its performance will change. Okay, the next mistake is related to the oscilloscope's offset. This indicator is ground or 0 volts. Up here is the actual 5 volt rail. When we change the scale knob, the signal goes off screen and the position knob cannot bring it back. The scope's front end has a limited dynamic range. We need a way to keep the signal within that range. There are 2 ways we can do that, and the first one depends on who made your oscilloscope. Turning the position knob on my scope changes its visual location. See how the screen says div and not something like volts. In the channel menu, there is a separate control for voltage offset. With this control, we add a DC voltage into our signal before it goes into the analog to digital converter. Some oscilloscopes do this voltage offset by default. Others do the visual thing like mine does. It just depends, so you might have to play around with yours to see which it does. Now, the other way we can get rid of that offset is by changing the channel's coupling from DC to AC. This control puts a series capacitor into the signal path, which takes out the DC component. The trouble is, it also removes some of the really low frequency stuff like below 10 or 20 Hertz. So I suggest use the voltage offset as your first option and only do AC coupling as a backup option. Now that we have the rail in the middle, we can crank up the sensitivity to get the noisy waveform to fill the screen. Remember, when using a scope, fill up the screen as much as possible without clipping. Next, move the trigger position to go slightly above the signal activity to help catch transients. Then turn the time per division knob to capture a few milliseconds of time. At this point, we have a pretty decent display and a good feel for what the rail is doing. To help, I like to turn on infinite persistence. Instead of the grid or cursors, I like using automated measurements. So here I turn on a peak-to-peak and RMS voltage for the DC rail, and then add an RMS current using a current probe for reference. With that, we can see the switch mode converter has about 266 millivolts peak-to-peak ripple noise when a load draws 1 amp. For a 5-volt rail, that's around 5% and a little concerning. Except, like the DMM, the oscilloscope is lying to us. Kinda. First problem is, in my setup, the full bandwidth with a passive probe is up to 500 megahertz. So we're measuring a ton of broadband noise that doesn't matter. Most oscilloscopes have a 20 megahertz filter built into them intended for power supply measurements. And just turning that on, then clearing the measurements, and increasing the sensitivity now shows the noise is only about 33 millivolts or 0.6%. Another problem is related to the probe. Remember, those are 10-to-1 passive probes, which mean they divide the signal by 10. We're trying to measure millivolts of noise, but the scope is seeing 1/10 of the original voltage. So, what can we do about that? For quick measurements or a first order, is this converter working well, a 10-to-1 probe is usually fine. However, for a better measurement, you want a 1-to-1 probe. Sometimes there are specific passive probes that do this, or you can switch a 10-to-1 to be a 1-to-1. Another option is something special called a power rail probe. These are a combination of an active and passive circuit that achieve high impedance, high bandwidth, high voltage offset, and have no attenuation. They tend to be specific to a scope's manufacturer. You connect them both into a circuit with either a passive-like browser or a solder-in pigtail. Both of these have a coax connection that plug into the probe's pod. As a solder-in, they can have multi-gigahertz of bandwidth, while the browser configuration limits the measurements to hundreds of megahertz. These probes do have a relatively small dynamic range, but can provide a huge DC offset compared to the one that's built into the oscilloscope. Rail probes are a high bandwidth probe. For example, this measurement is at 500 megahertz like the passive probe. However, notice that the peak-to-peak noise is less than 60 millivolts, compared to the passive, which was 260 millivolts. Also, if we use the 20 megahertz filter like before, the peak-to-peak is only about 20 millivolts compared to the 33 millivolts with the passive. So the rail probe is significantly better for measuring ripple voltage. Now, you might ask, if the connection to the probe pod is a coax, why not just plug the coax directly into the scope and avoid the relatively expensive probe? Well, that works if the measured voltage is low enough. In our case, the 5-volt rail is the limit of what this scope can measure. Also, the 50 ohm termination means the supply is being loaded by the scope and the cable-based probe. Another option would be the 1 kilo ohm soldering probes we made in another episode. If I attach one to our BAT converter and then look at that on the scope, we might see the downside. Remember, these have a 20-to-1 attenuation, so they aren't measuring the voltage as well as either the passive or the rail probe. But the upside is they're less capacitive and use the 50 ohm path on the scope, so we do get more bandwidth than the passive probe. Now that I've said bandwidth enough times, let's talk about that. 20 megahertz is the pseudo standard since most power distribution networks aren't very high bandwidth. So then why would you need a probe that has gigahertz of bandwidth? Well, in the era of IoT devices and radios, it is really important to know if your voltage rail is acting like an antenna or coupling those high-frequency components into other parts of the design. For example, the FFT of this board's voltage rail shows a small but wide blip around 750 megahertz, which is a frequency used by cellular radios. The spur is small enough it probably doesn't matter, but it's also something that you want to test for in your designs. If you're planning to sell your design as a product, then I highly recommend you get a rail probe for testing. For prototype or one-off work, they're not nearly as necessary. It's more important that you set up the scope correctly. Now, once you do set up the scope correctly, there are some other measurements that you can make. Before closing, there were a couple of measurements I saw while working with this converter design, so I wanted to show them off. First up, needs my magic wand. Here I have the switch mode converter connected with a load and scope probe on the output. Then I place a near field probe around the inductor. Looking at the scope, the purple trace is the EMI that the near field probe picks up. In other words, we can see the switching action without electrically touching anything. Near field probes are my favorite measurement magic trick. Okay, next I want to show something about duty cycle. The switch or SW node of the converter is right at the inductor. This time I am placing an actual probe to measure the actual voltage. Looking at the scope screen, we can see the duty cycle of the switcher. As I change how much current the load draws, the duty cycle changes along with it, all the way up until the point where we draw so much current that the switch basically just turns on and the switcher stops working. Also notice on this good converter how the edges are nice and clean. But if I switch over to the bad converter, you can see that there is a terrible resonance when the inductor switches on and off. And another way we can look at that ringing is with an FFT. Here there is a clear bump around 12 megahertz, which is the same frequency of that ringing. I think things like the FFT are pretty cool. The key here is that once you get the rail on your scope screen correctly, you open up the possibility for evaluating a switch mode power supply well beyond what you can do with a DMM. Measuring ripple of a switch mode power supply is just one measurement. There are also things like transient response, efficiency, and control loop stability. If you're interested in having those covered, let me know over on the Element 14 community. There you can find show notes related to these measurements, links to the tools, and that is the best place to ask me questions. As always, thank you for watching. For now, it is time for me to get back to pulse width modulating reactive components for a stable DC value on my electronics workbench.